G'day. Today we're going to do thermal baths for parts, or thermal loads. We're going to two-type: one where we immerse the entire part in a thermal environment, and then we should also run one where we put a thermal gradient across the part, where one end is a different temperature than the other. What I've done is got a model pretty much set up for almost everything here. If you want to follow along with me, the link is down below. For this model, you can download it and work along. Now if you want to, this is a version 14. If you want version 13, let me know and I'll make one so you can do this as well. It's pretty easy to do. What I've got is my components: green, red, yellow blocks. I've got some constraints on here. It's totally fixed. The end here and this support over here is allowed to slide back and forth, but not up and down. I have different materials for each of these, just so they're going to expand differently thermally, and properties for all of these are P solids because they're the three-dimensional item. Now the big thing under materials, make sure you have your coefficient of thermal expansion for each of the items. So I have one for steel, one for a polyethylene, and one for just epoxy. I just picked some values that are completely different from one another. Okay, to do this, what you need to do is create a load collector, and you call it whatever you want. We'll call it temperature. Call it temperature bath, and we'll give it a different color just for fun. Okay, it's under boundary conditions, create temperatures, so you can put in the value of the temperature. The default value, everything is at 0, so this is 50 degrees increase in temperature that I have here. So we're going to go with 50 degrees. You can type in whatever value you want here. The load type is temperature. We can put labels on, and we're going to create it on all of the nodes and hit create. So there they all are. They should be at 50 degrees. If we zoom in here, we have 50 degrees on each of the nodes. So the entire part is bathed in 50 degrees. So now we need to create a load step, and we're going to make it a linear static. I already have the SPCs defined. And now, instead of a load, normal load you put in, you go under temperature. So our temperature load right now is this 50 degree bath. And there we are. So now we should be able to run this. And I'll just pause this while it runs. It actually didn't take very long at all, so we're going to go and look at our results file. Here's our part. Turn on our contours. And there it is. So our deflections are of the order of a millimeter or so. We can increase them in size if we want and have a look at that. And slow our movie down and hit play, and we will speed it up. So that's quite a bit of deflection. Let's tune that down a little bit. There we go. And we'll watch the movie. Now you can see how it expands. This one's not allowed to move up, and it's fixed over here. Ta-da! There's your bath. Now what we're going to do is do the same basic thing, except we want to do a gradient function on this. So first of all, let's turn off, go and turn off those loads. Now we're going to make another load collector, and we'll call it temperature gradient. And we'll give it a different color. Okay, so to let you know how big this thing is, first of all, if we go and look at nodes, we can see over here the X value in this direction is 0, and over here If I click, it's 200. So my part is 200 millimeters wide. So let's say I want to do a 100-degree difference from one side to the other. So let's see if we can do that. Temperature increase of here is 0, temperature increase on the right of 100. So our temperature gradient collector down here is active. Boundary conditions, create temperature. And instead of a value, this time we're going to put in an equation. So here's one I was playing with, but let's say we want to do it 100 degrees. So we take every x value and divide it by 100. Okay, so when x is 0, this evaluates to 0, so we got 0 degrees here. When x is at 200 over here, oops, then we'll have 2 degrees. That doesn't make sense. X divided by 2. That's what we wanted to do. There you go. So when x is 200, 200 divided by 2 is 200. There we go. So the nodes we're going to apply them on are all of them. And there they are. You can see where they increase because the magnitude of the arrows is a percentage. So very small over here, very large over here. So if we go and look in at these, okay, we got 15 degrees there, 0, and each of these is increasing slightly, so we got 15 degrees on that leg. Over in the middle of the part, we're at 50. And at the end of the part, we're at 100 degrees, just so like we want. So that is a temperature gradient. Let's go ahead and we will just change our load step here. Under temperature, again, we got same SPCs, linear static. Under temperature, we're going to put in our temperature gradient. Done. So let's run that. And we'll be back in a second. Okay, so the gradient is done. If you want to look at the results for fun, we'll pull that up. And here's the results of a temperature gradient. It's as easy as that. I hope that was helpful. I'll try to put some more up. If there's something you want to see, just let me know. Thanks for watching.